Good evening.
Hello, good evening. My name is Magwang Dim Magwang.
My name is Benjamin
And,
Munji.
and today we are going to present our project, AI project. Our AI project is a knowledge graph reasoning clinical large language model for safe dispensing in resource-constrained Uganda. So we have a group of three, and so the content for our presentation today is we are going to introduce the related work, then problem statement, research questions and objectives, research contribution, methodology, and then dataset representation, plus results, conclusion, and future work. So we are going to dive in. So introduction is the problem. So problem, few pharmacies in rural Uganda, plus the risk like unsafe dispersing, and then need. So the need for this AI tool for safe and explainable decisions. Then the source is knowledge graph plus large language model. So the background for this project is we are using Ugandan clinical guidelines plus essential medicine list. Challenges: rural drug shops, semi-skilled staff, limited internet, and digital tools. So existing tools, we have some existing tools, but these tools are not for local use. So they're for high income countries. So we wanted to close a gap that can work offline locally, and then it can explain recommendation. So there are some related work to our project like CDSS. This reduces errors, but this this system only work in big hospitals. It doesn't go to rural areas. Plus the large language models in healthcare. It gives strong results, but there is a risk of hallucinations. And then there is knowledge graph, drug, drug disease reasoning, but it is not locally. And then we have AMR tools. This one only monitor, but it is not point of care. And then we have LMIC studies. This is unsafe dispersing in Uganda because we have few digital tools in Uganda. So we want to close a certain gap of local offline, and then our AI is going to be, it will explain recommendation that for rural people. So we have problem statement, problem domain, computation problem. So few pharmacies in rural areas, unsafe dispersing, and then existing tool, not locally and offline. So these were our domain problem we have come up with. So the computational problems, so is input. So the description and the guideline of the AI for the rural people and pharmacies. So, and then output. So our output will be like saved and then explainable recommendation that can be understandable by the pharmacies and rural clinics. So we also got some challenges like noisy data plus hallucinations and plus low resource deployment. So it will bring us to some research questions and objectives of doing this research. So the research question we came out with: how can AI support safe drug dispersing in rural areas? Can large language models plus knowledge graph reduce errors and AMR risk? How do we design for low resource setting? How can recommendation be made explainable and guideline based? So our objectives were to build a knowledge grounded large language model, which is locally guided by our way of living. And then we have model, drug, knowledge graph. So this is going to be interacting with our guideline and then the rules. So, and also we are going to implement RAG pipeline. this is going to be safe and then explainable, like they give good recommendations. And then we want to evaluate and train pharmacies in rural area so that they can give accuracy when giving out drugs. So while doing the research, there were some good contributions, like it will enable us to develop a clinical language model based on Ugandan guidelines. And then we are going to be able to build fast drug knowledge graph for, Uganda. And then deploy RAG plus KG reasoning pipeline. And then we evaluate, and then it will be safer and explainable for pharmacies to use it in rural areas. So these are methodology, like the flow of our work. So we're going to collect the data, then we try to process it, clean it, and then we train our model. After training our model, and then we deploy it, and then we evaluate how it will be working. So that is how. So we try to test our model. The data set we use was from breast cancer Wisconsin dataset. So the source was UCI machine learning repository. And then the purpose of this dataset was to predict whether a tumor is malignant or benign based on cell nucleus features. So the sample we carried out was like 569 rows, 32 columns. So the features were like 30 numeric tumor features plus diagnosed targets. So the target was malignant and then benign strength. So clean and no missing data. So the limitation we faced was small data set, mostly numeric. So this data set, and then we also got another data set of heart disease data set from Cleveland. So it was the same from the same source, UCI. So the features for this was, we have 14 features: age, sex, chest pain type, blood pressure, chloroteros, resting, ECG, exercise results. So the target was the presence or the absence of heart disease. So learning. So the suitability is supervised learning. So the strength here is more variable in features, numeric plus categorical. So we widely studied, so good for learning medical AI pipeline. So the limitations we got here was slightly more cleaning. Pre-processing is needed than the other two. So the sample size was 303 patients. So I will stop here, and my colleague will take the next part.
Let me share my screen. You can stop sharing your screen.
Benjamin.
You can stop sharing your screen so that I can share. So, hello everyone. Like I said, I'm Benjamin Munji, and I'm going to be taking you through the exploratory data analysis results and the model fitting and evaluation. So Deng, you can stop sharing your screen so that I can share mine.
Make it large.
So the exploratory data analysis. In this, the goal of the EDA is to uncover patterns, assess data readiness for modeling, and identify any risks or biases that could affect clinical decision making. So like our colleague said, we had two data sets and we narrowed down to the breast cancer Wisconsin for a few reasons that he has mentioned. And so in the EDA, we found that the dataset contains 569 rows and 31 columns. Each row represents a tumor sample with 30 numeric features describing cell characteristics, e.g. radius, texture, concavity, and target variables like diagnosis. So the target variable was diagnosis. The target variable, which was diagnosis, is binary, malignant for M and benign. Missing values, there were no missing values were detected in any column, which suggests the dataset is clean and ready for modeling without imputation or data repair. Descriptive statistics, the features such as area worst, concavity worst, and perimeter mean show high variance and skewed distributions. This may dominate model behavior and require scaling or transformation. Some features, e.g. smoothness, SE, fractal dimension SE, have very low variance, which may limit their predictive power. So the visualizations. In the visualizations, we have a histogram, a box plot, a correlation heat map, and count plot of diagnosis. The histogram reveals right skewed distributions in several features, indicating potential outliers or non-normality. The box plot shows that malignant tumors tend to have higher values in features like radius mean, area worst, and concavity mean. Correlation heat map highlights strong positive correlations between radius, perimeter, and area features, suggesting redundancy. Count plot of diagnosis shows class imbalance, i.e. 357 benign versus 212 malignant cases. So what was the interpretation? The class imbalance in the target variable means that accuracy alone is not a sufficient metric for model evaluation, and we will have to prioritize F1 score, precision, and recall to ensure malignant cases are correctly identified. The strong correlations between certain features suggest that dimensionality reduction or feature selection may improve model performance and interpretability. Skewed descriptions and outliers may affect model sensitivity, and so we'll have to apply standardization and consider robust models like random forests that are less sensitive to feature scaling. So this EDF provides a solid foundation for model training and highlights key considerations for building a clinically relevant classifier. And so without further ado, let us move to the model selection and deployment. So here we did some model fitting and evaluation. And so the model choice was random forest classifier for this task. Given the binary classification problem, malignant versus benign tumors, random forest offers strong performance with minimal tuning and built-in feature importance. It's also interpretable, which is critical in clinical decision support systems where explainability matters. The model architecture and parameter. Like we said, the model is random forest classifier, and the key parameters are N estimators, which are 100, number of trees in the forest, random state, 42, which ensures reproducibility. Preprocessing. Features were standardized using a standard scalar. Target variable was label encoded, i.e. malignant is one, and benign as 0. So the evaluation metrics were F1 score, like we said, precision and recall, and confusion metrics. F1 score balances precision and recall, especially important in medical diagnosis where false negatives are dangerous. And precision and recall were used to assess the model's ability to correctly identify malignant cases. The confusion matrix was used to visualize true versus false predictions. So the results and interpretation, the model achieved a 91% accuracy. The F1 score, malignant, was high, indicating strong performance in identifying cancerous cases. Confusion matrix, very few false negatives, which is crucial in clinical settings. So the limitations were, while the model performs well on this clean, structured dataset, real-world deployment in rural Ugandan clinics will involve noisy, incomplete, and handwritten data. This highlights the need for robust preprocessing, e.g. OCR pipelines, semi-supervised learning for partially labeled data, and graph-based validation to ensure clinical safety. And so let us jump to the integration of the core AI concepts. And so this project integrates foundational AI concepts to build a clinically grounded, explainable assistant for pharmaceutical decision support in rural Uganda. And so here is a breakdown. Learning, we used supervised learning to train a random forest classifier on labeled tumor data. This approach is ideal for structured datasets where the target variable, e.g., benign versus malignant, is known. In future stages, we will transition to semi-supervised learning to handle noisy, partially labeled prescription data from rural clinics. Then the types of intelligence, we have our AI model will have linguistic intelligence, which is used to interpret text, which is used to interpret prescription text, dosage instructions, and clinical guidelines. Logical mathematical intelligence, which applied in reasoning about drug interactions, contraindications, and dosage calculations using structured clinical guidelines. This dual intelligence allows the system to understand both human language and medical logic. The data mining techniques, we apply classification to multiple tasks, predicting tumor type, i.e. benign versus malignant, determining whether a prescription is safe or unsafe, flagging potential contraindications or dosage errors. These tasks are central to building a reliable clinical support tool. Then we have knowledge representation, where we represented pharmaceutical knowledge using a drug knowledge graph where the nodes were drugs, conditions, dosage rules, and the ages or relationships like interactions, indications, or contraindications. This graph structure enabled structured reasoning and contextual retrieval. Then we had reasoning. The assistant performs reasoning through graph traversal and large language context injection. This hybrid reasoning ensures both accuracy and transparency. Philosophical framing. The system is framed as weak AI, a task-specific tool designed to support clinical decisions, not to mimic human consciousness. It addresses a firm problem by grounding its outputs in curated medical guidelines, ensuring that its recommendations are contextually safe and medically valid. This integration of learning, intelligence, reasoning, and philosophy ensures that the assistant is not just accurate, but also explainable, ethical, and locally relevant. And so we move to the conclusion where AI can improve safe dispensing in rural Uganda. Large language models plus knowledge graph are explainable, guideline-based will lead to explainable guideline-based recommendation. It will help reduce errors and AMR risk. Offline fast design will be practical for low resource settings. The limitations and suggestions, we have limited data, i.e. few digitized prescriptions available in Uganda. The solution would be to expand data collection, partner with clinics and the Ministry of Health of Uganda. The model hallucinations will be the large language model may give unsafe advice. Solution, enforce KG-based rule checks and human in-loop validation. Resource constraints, we have limited devices and connectivity in Uganda. So the solution is use lightweight language models plus offline deployment. Language barriers, i.e. many patients prefer local language. So the solution would be to incorporate multilingual or voice support. The future work, maybe we can talk about the future work. Our next steps are to expand the data set, collect, obviously this was a very small data set, so we are planning on collecting more prescription and real-world dispensing data. We're planning to improve knowledge graphs, I add more drugs, interactions, and AMR rules, enhance the model, I test other LLMs and stronger explainability features, pilot deployment, test the tool in rural clinics, and gather feedback. The future direction and recommendations include scale to other LMICs with similar pharmacy challenges, support more local languages and voice inputs, stronger governance, privacy audit logs, AMR dashboards, integration with health systems, i.e. linking with the national e-health platforms, research direction, explore causal AI plus graph reasoning for safe drug interaction. So this is a brief about our language module. Thank you so much for listening to us, and don't forget to like and subscribe.